Right, so today I thought we'd talk about a little bit more about the homework and then generally about threads and what we can expect from threads and about synchronization and sort of the interaction of multiple threads running on multiple cores potentially. Okay, so first of all I got the bugs fixed in the template. Who's gotten started on the homework? I know you got started. He doesn't want to brag. Anyone else doesn't want to brag? Anyway, so yeah, the homework template is updated and seems to be working fine now. There were some more little nasty details with the port to 64-bit that I had overlooked and ran into now with the multi-threading. So maybe to start out, why don't we try taking the homework solution for a spin, just to see what it's supposed to look like, and we can take a look at the description while we're at it. I've updated that. It's on the website. Let's see. So the very first thing you want to do is just get, like, when this first program, what's it called, thread 1, when this calls thread create, just make it run F. Instead of printing hello from main, just make it run F. It's not too complicated. Basically, you just reassign the RIP and the trap frame to F, and it should work. And then from there, you know, there's multiple steps, multiple small steps that you're suggested to take in the homework description, which eventually leads you then to complete thread implementation. Yeah, so this is the first one, right? Just get it to run F instead, and then you know, let's just fork instead. So clone is almost like fork. It's very similar, except when you fork, you get a copy of everything instead of just a copy of the things that are local to a thread and then a pointer to the rest of the old process. So you could start by basically using fork, but making the copy run F, right? And then finally, you want to make sure to have them use the same process. Right? And so that should be mostly a question of reassigning a pointer. All right, so let's just see what this is all about. So I'm running this here with SMP4. I highly recommend that you run with more than one CPU. So the SMP is simultaneous multiprocessing. Basically, it at least emulates having multiple cores. And you don't have to have multiple cores in your machine. It'll just do something to make it feel like you have multiple cores. It actually runs a lot slower whenever you emulate multiple cores. So I presume that by default it's running it all on one hardware core in my machine, but I'm not sure about that. Okay, good. Yeah, so that's a good place to be. All right, so let's just run this thread 1. Oh, I'll use this. Thread 1. So as in the code, right, it prints out and then there's a while loop at the end, and the reason for this while loop is that it would crash otherwise because you haven't implemented thread exit yet. So these threads, they don't know what to do. Okay, so there's two things that could go wrong here. Like one, if we don't have this one, you run through here, and now where do we return to? Well, there's no place to return to. It's going to be a little weird. So F has to thread exit. And then main here, if we didn't have this while loop, well, main knows where to go. Actually, we could just put exit here instead. Main doesn't know where to go now. There's no exit. It also needs to die. But we could replace the while one with exit, except then you would end up with, without having made any changes to your thread implementation, you would end up with this F here relying on the process that was created for main But that process was now cleaned up. So again, that wouldn't work. So there's several steps that we need to take in order to be able to just run the program to completion. Okay, so that one at least prints out both things. That's good. And then let's see what else we have. Oh. Thread 2. And so you see there's several test cases here. And basically we just want to run each one of them without crashing and producing roughly the expected behavior. So this one demonstrates that there's shared memory. It continues up to 10 million, I think, but we can stop it here. So here we have one thread that's plussing, and the other one is just printing it out. If it's changed, it just prints it out again. What is that? 10 million, right? But then we have the while loops at the end because we still haven't fixed the exiting part. All right, let's try out. Actually, we should take a look at the code first, maybe. So in this one, I think it's thread exit that we're dealing with. Yeah. So now there's no while true anymore. And this one ought to call thread exit at the end. You're not allowed to change f. And that's a common problem with homework turn-ins. You sneak in a thread exit over there, and that's not allowed. We don't change the user programs. You may change the user programs all you want when you're testing things. Sometimes that's a good idea. You know, you might want to try putting in a thread exit for a little while to make sure it works. You know, to make sure your system call thread exit does the right thing. But then you want to delete it and make sure that you have thread exit on the stack, so that the return here jumps to thread exit on its own. Okay, so I think this one does all the same things, except it runs thread exit at the end. So in fact, to make this go a little faster, I will just go with SMP1. Oh, but it doesn't print out along the way. That's the difference. All right. So that one finished without crashing. That's the main thing here. I think that it doesn't get done unless you see. Yeah, okay. So it doesn't print out. It doesn't get done unless shared goes to 10 million. So it still needs to have shared memory. Yeah, okay, so this is interesting. Right. It doesn't actually handle the exit very well yet. Right. Now we're supposed to thread exit first, and then this program will exit. And that's safe. As long as there's no other thread running, we're okay. But exit we need to handle a little bit later on. This is one of the things that that's common with threaded programming. Race conditions, where you have two programs that should, two threads that should execute things in a certain order, but they end up executing in a different order, or somehow interleaved in a way that you didn't expect. That's a race condition. In this case, it doesn't work to do it this way. I'm telling it to wait for what is that? It's so hard to read these things on the screen. Well, it's maybe 1 billion times around the loop. Yeah, 1 billion times around the loop. You can't actually trust that thread 1 will finish, or that this F will finish before main does. Because there's no guarantee about the speed at which threads execute in hw6 or anywhere else. You almost all the time, main will wait until until the other thread is done. But you know, one time in 1 billion, that's the time when you're flying people on the spaceship. You know, it'll do it wrong, and then you have a big problem on your hands. So here, in order to get this right, exit should verify that there are no other threads before finishing up. Or you could have a condition variable, if you've used condition variables in threaded programming before, you could say, wait until this thing is true, right? And have the other thread notify, well, I'm done. Right? And that might also be okay, depending. That's essentially how exit would have to do it anyway, inside of the system call. Okay, so we ran that one, and then there's thread 3b. And that's this exit semantics. So let's take a look at 3b. And here we don't have that loop anymore. So now it should do the same thing and still not crash. Right? And this only works because exit was waiting to make sure there are no other threads running. All right. And then there's thread join. So now we, let's see, what's it say here? Let's take a look at thread 4. Yes. So here we're, from user space, we have a similar ability, right? So now we're able to say, let's not continue running until f is done. So that can sometimes be useful in a user program. In this case, we want to see what was the value of shared at the end. Of course, this program would not crash, even if thread join didn't work. If it didn't do anything, this program wouldn't crash because we implemented exit correctly. So it doesn't clean up before. But it would print out the wrong value of shared. So shared really should have gone all the way up to 10 million. All right, so let's try that one out. Thread 4. Right, and then there's several versions of this one, if I remember correctly. Yeah, so now this f actually finishes long before main does, and thread join still needs to work. Right, so it shouldn't kind of wait forever because the thread isn't like sort of finished before we started waiting. And then let's see. C. Here we make very many threads. So there's 50 threads, and we just want to join all of them. And that also needs to work. And then in thread D, it's the same story, but here I think the main doesn't. How was it? Well, it's a different ordering, one way or another. Like the threads are expected to finish first, something like that. So we'll just, I think we'll just skip those. Okay, and then finally for thread 5, there's this exec. So let's take a look at thread 5. I think there were no, there's only one thread 5. But there's the helper program that we're running. And so, right here, the main thing is we have a thread that's running in the background, but then when we run exec, that thread shouldn't be running anymore. Right? You could imagine leaving the thread running. That's just not correct operation. And of course, it can't be crashing or anything. So let's just make sure. Right. So it's running. Okay, well, let's see, what did it do? At the very top, there ought to be something else. Now running instead, okay. In fact, I'm a little confused. Okay, yeah, so basically we're running a new program and exiting, and that just should be fine. We shouldn't have this other program, the other thread, doing much for us. I think it went a little too fast. If we do it a couple more times, maybe we'll see that it actually gets to print something out. See here, I have a 10,000 long wait. it should be enough time that this one gets started. But it wasn't enough time this time, at least. So I ended up running exec before even this function got going. Let's try it one more time. Nope. All right. So if I put a longer wait in there, that'd probably be fine. I think we'll skip that. So I would highly recommend that you play a little bit with these wait values, just to kind of make sure that your thing works under various different conditions. So run a different number of times around these loops. Run 1,000,000 times instead of 10,000 times, and there's many different orderings for everything here. Right, and those orderings may well appear on Nilanjana's machine, but not on yours, unless you try different orders yourself by enforcing it with these waits. Questions? Okay. So yeah, generally just if you just follow these steps, one step at a time. I try to lay them out in a way to make it relatively straightforward. It shouldn't be too hard, at least to make some initial progress, and then I think the hardest part, at least for me, ended up being the exit, the sort of the semantics of who's waiting for who's responsible for cleaning this up, and because there's many different threads calling exit at the same time, and so on. Okay, so with that, let's switch to just talking about threads in general then. I think you've all probably done a little bit of pthreads programming, and hopefully you've gotten some sort of exposure to concurrency in general, but it doesn't hurt to repeat these things a little bit. In fact, I'm hoping to teach a class only on concurrent systems in next fall, but we'll do just a mini version of that in the next couple of lectures. So. Right, and then a reminder, I am not here next Tuesday. It'll be only online, that lecture. I'll be in Shanghai. All right, so threads. There was it's a beautiful quote, see if I can find it. Oh, here it is. Oh, it's not a quote, it's a little story. Programmer had a problem. He thought to himself, I know, I'll solve it with threads. He now problems too he. Has no problems too he, yeah. That pretty much captures it. Threads make things hard. They seem to make it easy, but they usually end up making it hard. So why do we want to use threads in the first place? Any ideas?
CPU manufacturers are making more and more processors that are getting much faster. They're just making more cores in each processor.
Right. So you can buy processors with 8 cores in them. And why do we need threads for this?
To get the full use out of the core for one program for the CPU.
That's right. We can't run one thread on multiple cores at the same time. And we have many cores, but the cores aren't really going any faster. That's exactly right. So now we want to run a program faster. That's really the only reason to use threads. It won't get any faster on a single core. You can always write the program some other way, and usually it's a good idea to write it some other way if you're just doing it on a single core. But on a multi-core machine, we don't have much choice. There's several different weird multi-threaded architectures out there. The main one that everyone pretty much has is the standard multi-core processor. It looks, I'll steal a slide from my presentation that I was working on. Let's see. Hello, here. Okay, so this is generally what you might expect the sort of the interior architecture of one of these chips to look like. So this is a single chip. It has like hundreds of little pins on the bottom, right? And that connects to the motherboard that has the memory and so on. This is all this little black thing with a big fan on it. This one has 14 cores, it looks like. Each one of, oh, no more. There's one, oh yeah, each one of these is one core. So there's some interior bus for communication between these cores. They each have a little bit of the shared cache, the last level cache, that they control, and there's this bus in between to talk to it. And then they have their own caches, the L1 and the L2 caches that you may be familiar with. And then there's one or more memory controllers that hang off of these buses that then talk to the DRAM, the RAM that's sitting on the motherboard. And there's some other for talking to peripherals. So the PCI bus, sometimes for USB, there might be a separate one. Sometimes for a link to other CPUs. If you have multiple, you can have multiple chips as well on your motherboard, and then you'll need small here, but it says a QPI link. Usually they draw it like this for a larger system. This one with four different chips, and there's some sort of link between the chips, as well as the links that go from the chip to the memory, and from each chip to the various peripheral buses. So anyway, if you now want to run on this 18 core machine, you'll want to run a separate program on each one of these little chips, and those are our threads. Of course, there's no guarantee that one thread runs on any given core unless you specifically tell the CPU only run this thread on that core, which you can on most OSs. But generally that is sort of controlled by the CPU. There's also no guarantee that the thread will run for the next foreseeable future. It's just, at some point, it will run on some core. Usually, it'll be pretty soon. But, you know, the machine might be busy doing other things for a long time. Okay, so threads. Purpose, almost only to make use of parallel hardware. All right, so by parallel hardware in this case, it means we have all these different cores. There's also other types of hardware. There's the Intel many-core architecture. Let's see if we can get a picture of that. What is it called? MIC, that's the old name. Well, it looks something like this. Yeah. So Intel is going a little crazy. They're taking like their basic Pentium processor, Phi, that's what it's called now. This is a picture of one of those dies. So they put hundreds of cores on one of those chips. Same thing. Basically very little, each core is very slow, but then you have very many of them, and in the end, if you write a very many threaded program, you'll do fine. Oh yeah, this one says 80 core. All right, but I think they're going to go much higher than 80. I think. Yeah, so these actually run their own. They can run their own Linux if you want. Like they're a proper CPU. In a GPU, usually you end up with very limited functionality, and oftentimes it'll have one stream of instructions that operates on many different copies of the data, and it's it's a very different programming model. In fact, I think I saw one of these. I've never worked with these, but I wanted to buy one. Actually, let me just see. Xeon Phi. This is a PCI. So you plug it into a normal machine, and then it sort of gets a virtual network interface, and then you can kind of get it going from there. If anyone gets an A in the class and then wants to do some research project with me later on, I'll be happy to purchase one of these, and we'll try it out. Let's see, how many cores does it say? Well, this one maybe says some. What? 61? No, I've seen much better than that. Anyway, so yeah, they come in different scales, right? The machines that we usually work with for my research is just large high-performance servers with say 64 cores on one or 32 threads on one chip, and then we have 4 chips. So it ends up being 120 threads or so, 128 threads. In a normal computer, you would expect this one maybe has 8 threads, 8 hardware threads and 4 cores, I think, probably something like that. Anyway, in order to go fast, we will need to use threads. Sometimes it's to write more intuitive code. Right. So a thread can be a description of an interaction with one other client. So if you're a network server or a web server, you might get several requests from a client, and you might want to keep those all in one flow. And then you have multiple such threads, one for every client that's on the other side. And it gets so much easier if it's one thread. You know, you have local variables, let's say, that are associated with this client. You have an ID already associated with the client. Everything just makes sense. When you're waiting, you're only waiting for one client, so when you get a response, you know it's from that client. You don't have to worry about it. An alternative is to manage all of the concurrency yourself in an event-driven program or with asynchronous callbacks and all this like they do in Node.js and so on. And that's also okay, but those tend to be harder to write. As long as you don't have much shared state between the threads, you know, everyone has their own, just working on the stack, let's say, threaded programs are super great. It's very easy to work with. It's when you start having global variables that you access at the same time that it starts getting hairy. Okay, so problems that we end up with when using threads usually have to do with access to shared global state. So we could end up with, most likely we'll end up with race conditions. This is timing-based errors. So a thread, there's no guarantee. We know that a thread will operate its instructions one after another. In fact, there's some limitations to that statement too. There's, you know, a processor runs instructions out of order. A CPU compiler might not generate code that looks exactly the way you wrote it, but generally things behave as if it all executed in order. So the CPU will try to ensure that, and the compiler will try to ensure that for a single thread. So any single-threaded program you write, you can safely assume that all the instructions you wrote will execute in the order you wrote them, which is really nice. Single-threaded program executes in order. That's good to know. Now, if you have more than one thread, we know that they will both, on their own, in isolation, execute in a certain order. And if all they do is write, well, then if they write to shared state, then we already have a bit of a problem. Because there's no guarantee, while there's a guarantee about the order of the instructions, there's no guarantee about the timing. So you might end up going quickly here and then slowly on this one, or you go, you know, kind of jerky down like that. It could be any sort of interleaving of the two instruction streams that you can imagine. And so that will create all sorts of problems. Let's see. Oh. I was hoping to get my little plot up here just in case, but the plot is not showing anymore. Let's see if it's hiding somewhere. Too many freaking windows. Hold on. I'll restart this. Nope. Okay, never mind. Forget your live feedback is not working. Okay. Where were we? Right. So we were running these. We have two programs, and they don't actually interact. Now we have two threads. They're just writing to some shared state. But the order in which those writes happen is a little bit unclear. So let's take a couple of examples. First case, we have two threads. One of them writes x equals to 1, and the other one writes x equals to 2. And then, after they're all done, we print out the value of x. There's no way to know what the value is going to be, except it's going to be either 1 or 2. Right? What if we take another example? So we'll start with y equals to 12, and then we'll say x equals y plus 1. Now we actually have a little bit of, potentially a bit of reading. Y equals y times 2. Yeah, okay. So now there's a little bit of interaction between these processes. So what's the output here? What is the value of x and y when this is all done? It looks like y has to be, no matter what, y is going to be 24. But x could be 13 or it could be 25. There's a very classic example which I'm sure you've seen before. So, okay, let's say x equals 0 initially. And so what are the potential values that x could have at the end? So we could end up with 1. Let's see, we could end up with 2, of course, because we increment it twice. But how do we end up with a 1?
When it starts doing the increment, they could possibly both be at 0, and then when they return, it overwrites the 1 both times.
Exactly. So x plus plus expands to move x to RAX, add 1 to RAX, move RAX to x. So we don't know in which, so we have two of these, so we could end up with both of those two executing first. So now we have a 0 in RAX in both, and then we, in some order, do the rest. In either case, we'll end up with a 1 in x in the end. So this is actually typical. Right? If you run a program where you do this sort of x plus plusing, we could write a simple example. We're always going to have this kind of problem. The only case where you wouldn't have the problem really is if one thread gets lucky enough to kind of, actually, why don't we, let's see. I think we can write a simple program quickly. Let's see. Let's do sort of pair programming here. When you spot problems, let me know. I think it goes. See. All right, I'll just do it like that. and I'll create a couple of threads. That's not necessary. And F. All right, let's see. What are we missing here? I think pthread create needs something more. It needs a 0 for some attributes. And maybe another 0. All right. Where was I? In Linux. Okay. In fact, we may as well do it in Linux. Probably a little more reliable. Reliable in the sense that I usually do Linux programming, not OS X programming. What are we missing? Oh, it's just warnings. Never mind. Look at that. Okay, so I'm doing 1 million increments twice. That's pretty cool. Aha, okay. I forgot about one thing. Very good, very good, very good. I like this exercise. I won't tell you why. I'll tell you what happens. But okay. So we're doing 2 million increments. We ended up with 1.2 million, 900,000, 1 million exactly, and 1.1 million. And this is beautiful. It captures so many different problems in this program. I must say I'm pretty pleased that we didn't get any compilation errors. Warnings are okay. So, so what happened? Let's start with this one. We already talked about that one. The problem is just that it expands from what looks like one instruction into 3. Now, there is actually an INC instruction in the x86 architecture, but for some reason it didn't use that. Let's take a look.
It's exclusively that, though, for that first one. It's also that the main exited before the, or did they?
That's it.
Wait. Right. So when main exits, then it's not gonna finish the rest of it in the thread.
Yeah. So in this case, it looks like the main thread got almost all of its increments. In fact, it got all of its increments, but some of them kind of got cancelled out by this other guy, and then main exited, and the other one didn't get to finish. If the other one got to finish, there's no way we would get less than 1 million. It's just not possible. And then we got, what happened here then? We got exactly 1 million. Did we get extremely lucky?
The red never executed before main exited.
This thread never got started, yeah. Main just did its million increments and then went on its merry way. And then we're back to sort of what I would expect is the normal state of affairs here, where you know, they're both running for some time.
Do you want to put like a wait and see how close they get without the...
Oh, you want to do like this?
Yeah. So I feel like if it's just collisions itself, it's going to be closer to like 1.9 million.
Let's do it.
A lot more variety.
But it's never going to go below. In fact, it can still go below 1 million, right? Because there's no guarantee that F will even finish. F will even start. But it's very likely that F will start when we have such a long wait. If we want to make sure that F finishes before we print something out, we have to do a thread join. think it goes like that. Ah. Okay. Do not program like this. Ah! Oh yeah, this is fine. Yeah, of course. So that's another way to make sure that we never get less than 1 million. But we're still getting, unfortunately, less than 2 million most of the time. Sometimes we get 2 million. How does that work?
Main, it's
Let someone else answer.
One option is just that they are one after the other. I mean, main runs first, after the other thread runs first, and then the other runs. They're
Right.
not overriding each other, basically.
Right. So main runs first, and then the other thread runs. So if we go like that, oh, now we're forcing that to happen. So now it's always 2 million. Because now F will not, this call to F will not happen until the other one is done. It's the point of joining. We're implementing a thread join, not p-thread join. There's no difference other than p-thread being a little more sophisticated. The parameter here, by the way, is a pointer to a return value. So from thread exit, looks like thread exit will take a, like if you return something here, this is an int perhaps, if you return something, you can get that out of into that pointer if you want. If you pass in a 0, nothing happens. Okay, but let's not do it this way. The join is good for safety, correctness. In fact, anytime you pthread create, you should have a matching pthread join. Just because it's no good to exit before your threads are done. Okay, so if we want this to be safe, what do we do? Actually, before we do that, I wanted to take a look at the assembly. And before we do that, look at this. I wrote this thing, and it doesn't, well, other than some warnings, you know, I don't get that. I didn't link with pthreads. I didn't say any pthreads, and it's not complaining. Why?
It expects, I mean, it might think that it's a shared library which we can actually load it.
Nope. So if you go like that, it says, what's this pthread create? All right. And if I go -c, then we're okay. Because -c, that makes a .o file.
yeah.
Right? And so the linker doesn't get involved when you do a -c. A -s is even less than a -c. That just assembles the C file. It doesn't care what this, what was it, pthread create is. Right? I'll let the linker deal with that when the time comes. X++ dot S, a little big, little s. And I wanted to see our F. Okay, so we're moving global to EAX, adding 1 to EAX, and then putting it back. This is 64-bit code. Usually, you'll see a lot of this is relative to your instruction pointer. So all the globals have a relative address. That's fine. And then, why is it EAX if it's 64-bit?
The compiler optimizes figure it does not need a 64-bit value.
It's not slower to use a 32-bit value, it's still a register. And why is it 32-bit, by the way? How does it decide that that's fine?
What is the concept?
This is the global value, right, that we're dealing with here. It's not the for loop.
Well, I'm saying the compiler could infer the max size of the for loop there.
Ooh, infer the max size of the for loop. Wow, we're getting pretty advanced here. Or we could just look at this,
Oh,
And see that that's a 32-bit type, right? So it's moving it to EAX not because it's optimizing anything, but because that's the way to do it correctly, right? We're saying this is a 32-bit type. When we increment more than 2 to the power 32 times, or 31 times in fact, it should be a weird value. In this case, it'll be a very large negative value, right? And that's the best way to do that. It'd be very complicated to achieve that with a 64-bit operation. Anyway, it expands to all these three, and so therefore it's obvious even from the assembly that this is not an atomic instruction. But in fact, there exists an instruction called inc that increments a global value. And so if we use that, it would look like a single instruction. But that's still not an atomic instruction. Inc will read the value. It'll end up in a cache or a local register one way or another in the CPU. And while it's holding on to that, someone else can read the same value. It's still not safe. If you want it to actually be safe, we have to have a lock inc, an atomic increment. So there exist several atomic instructions in the x86 instruction set. I think lock inc and lock exchange being the two that really matter. We use those for implementing synchronization operations primarily, but also in other sort of data structures where we need where we want to manage consistency some other way. So anyway, if we want this to work correctly, we have two choices. We can make this atomic increment, or we can use a lock to form a critical section around this increment, and then we'll be safe. Yeah.
Why not just use the atomic increment as the three instructions?
Yeah. In this case, it probably would make sense to write, atomic inc for whatever that creates, and that makes assuming that creates the atomic increment for the assembly. In general, the compiler doesn't know to do that, because we just said we want to increment it, and it doesn't know that this is a global variable, even though it's named global. Right? It doesn't. It knows that it's a global variable. It doesn't know that it's accessed by other threads. The compiler doesn't really know about threads. This is thread create is not a C language sort of thing. It's just a library function and a kernel construct. So we would have to tell it that, use a global increment. That's a good idea. But what if you want to do a multiplication? There is no global multiply. There's no atomic multiply. There's an atomic increment, but no atomic multiply. So in the general case, you can't use atomic instructions. There's another reason why you shouldn't use the atomic increment. That is dog slow. Everything atomic is really slow compared to non-atomic operations, so you can't just sprinkle them throughout your code. But of course, the only way to create a lock is to use atomic instructions. At least the only sensible way to do it. And so let's look at how that's done. But we'll start by just using it. Like that, I think. Yeah, I should initialize it somewhere. I can't set it equals to 1. It's got some other state in it, so it goes pthread mutex init. All right, I think that'll do it. Let's see. Should we fix this maybe so it doesn't spew so much errors, so much warnings? Little better. That wasn't better at all.
If you're calling out without,
Yeah.
you'd have to pass like a what?
Yeah, I'll put a 0. And okay, what do you want? So then that. Takes a mute, and then what does it take? Why is there no man page for this? Maybe sometimes it goes like this, and I have no idea why. Okay. Okay, fine. We will break out the big guns. Here it is. It wants a 0. Yeah. Some attributes. There's a few different ways that you might want your lock to behave, but let's for now just go simple and give it a 0. Yeah. Okay, what now? Aha. And fine. And is it? Yeah, it'll probably require this too. And probably gonna get another complaint over here. All right. Now.
Complaint about typecasting.
Yes. Let's see. What were we doing?
Locks.
Ah, yes, we were acquiring the lock. Very good. So now we don't know in which order the two threads are running, and their critical sections, being these little pieces, could be interleaved in any order. But at least we know that this global plus plus will not be interleaved in any way. All the code between the lock and the unlock will appear as if it ran atomically. So the point of this mutex lock is to wait until whoever was holding the lock before has unlocked it, right? That way we don't run the critical section at the same time. So it's important to realize, and sometimes when you talk about locks sort of abstractly and in the context of data structures and so on, you think that the lock is somehow associated with a data structure or associated with a critical section. It's not really. There's some sort of association here. We are manually protecting this part of code, which we call the critical section, by acquiring this lock, but the lock could be used anywhere else as well. All right, so that's one way to do it. But how does one implement a lock? So what we have at our disposal is basically a couple atomic instructions. There's two that really matter: the lock inc, atomic increment, and there's the lock exchange, the atomic compare and exchange. And at least in hw6, we use the lock exchange. So let's take a look at that one.
Is there an atomic decrement?
Probably. Not that I would really be using it for a lock. Let's see. Yeah, we can forget this now. There's a few other atomics too, I think. But generally, you would only want to use them for implementing synchronization operations, and you can get by just fine with just compare and exchange. On some machines it's called CAS, compare and swap. Others it's called test and set. But they all perform the same thing. Read the value. If the value is what you said, then change it to something else, essentially. So let's see. yeah, let's start with the exchange. All right. So I don't know, did we do any inline assembly before? Did we talk about inline assembly? It has a very complicated syntax. So maybe while we're at it, we'll just take a brief look at what's going on. So far, we were just doing assembly in its own file. Right? And the interface is pretty obvious. This is just the symbols. Right? These labels will be available from C. You can jump to them if you want, or call them if you want. That's about it. But when you write assembly in the middle of some C code, you want the assembly to have access to your local variables. But assembly doesn't know about C necessarily, and the C doesn't really know what you're doing in the assembly, so how do we make that all work together? So there's a few pieces here. I wonder if we have an easier one to start with. Never mind. So the top part here is the code. Whatever goes before the first colon is the code. So here we're saying just a lock exchange with two parameters. And these are going to be replaced by whatever is written down here in the constraints section. So here we're saying we have an input. So, let's see, actually, is it? Yeah, we have two inputs. So between the first colon and the second colon is a bunch of inputs declared. We have one that we're writing. Let's see now. What's a new value? Aha, okay. No, it's the other way. It goes outputs first. Yeah. Outputs and then inputs. So the 0 and the 1 here refers to adder and result, I think. And where's the new val coming into it?
Professor?
Yeah.
An easier inline assembly example would probably be the switch UVM function.
Switch UVM. Okay, let's take a look at that first. That's good. Thank you.
Like moving some value into CR3.
Oh, but then it may, that's not the one you mean. You mean the LCR3. Yeah, that one's way too simple. But why not start with that? Yeah, it's a little too simple. Okay, so I think it's probably better that I point out a nice tutorial on it. But basically, the way it goes is we have the code, and then we have some inputs, some outputs, and some inputs. We're saying each one of these positional parameters come from something in this list. So here's our first one. We're saying in a register, this constraint says where would the value appear. The value val should appear in a register, and then we put the register's name over here. So we're telling the compiler, you're fine, like take this val that I passed in, stick it in any register, call it EAX, and then replace my %0 with EAX. So we're not being too strict on the compiler about what it should do. We're just saying I need it to be in a register. All right, let's go back to our the compare and exchange we're doing. So exchange says, here's a variable, this one, adder. This, right? This variable, we want to replace it with a new value. And it'll tell you if the value didn't have that, if the variable didn't have that value already, then it'll set the value to that variable. But if it had the value already, then it'll tell you it had that value. So it returns the value of the variable always, like the previous value of the variable. And then if it didn't have the value that you were trying to set, then it will set it to the value we're trying to set. So we use it for locking. We say, okay, let's try to set the lock to 1, as in acquired. Now, if it's 0, if it's not acquired, it will get set to 1, and we get a 0 back, saying it was unset. So that therefore it is now set. Alternatively, if it's taken, then it won't do anything. It'll return a 1 saying it was taken already. Right? Okay, so that is all done atomically. The CPU guarantees that no one else gets to see the same unset. Right? So you never have two CPUs at the same time claiming this to set this value to 1. It's slow-ish. It'll take hundreds of cycles instead of a normal exchange would take 1 cycle. But still, that's only a fraction of a microsecond. So it's not that we have to worry about performance unless we're really worried about performance.
Is this GCC specific?
The syntax for the inline assembly, yes. But it's very similar to other inline assemblies. So we have, all right. So these are the outputs. The first part says, okay, in these variables we will be writing. So we're writing to this variable, adder. We're writing to this local result, right? That will be the whatever comes out. So that'll be this. And I think we must also be, aha, huh. I don't really get where we're getting the new val into this. Oh, of course. Yeah. So these are the parameters that we're using. This is an equals here. So we're just saying, oh, the register A will be overwritten. So this function here overwrites register A, and we should treat that as the variable name result. Interesting. Anyway, so if we look at how this is compiled, maybe we should do that. I think that'd be interesting. Let's see, kernel. Here. This is pretty cool. Pretty weird, unoptimized code, I would say. So here we're doing a lock exchange, and this it expects to have the value, the new value in EAX. I think that probably was set somewhere. I don't know how that ended up in there. That's okay. And then the return value out of this lock exchange ends up in EAX. So we store that in our local variable, right? The result. And then to return it, we have to put it in EAX. So we take it back from the local variable into EAX. That's very nice. And then return. Of course, when you run if you run this with optimization, if you do GCC minus 02 or 3, then these two would disappear because it's the same thing. Oh, yeah. Here it's sticking. Yeah, okay. A little unclear on the syntax. I always am. The last one is interesting. This one says which registers are being overwritten by whatever you're doing in the assembly. Because the C compiler, it'll just use registers for whatever it needs. Like for local variables, it'll keep those values in its registers, and then suddenly comes some assembly, and the compiler doesn't really know what we're up to in the assembly, because we might be doing, ints and other weird instructions that C doesn't know about. And so in there, we have to say, what are we going to be overwriting? So if in here we were saying, oh, move something to EBX, move something to ECX, right? And we have to say here, EBX and ECX got overwritten by this code. So the compiler knows that before entering here, it should save whatever is in EBX and ECX if it thinks it'll need it later. That's called a clobber. So here, this is the carry flag, I think. It just says you know, if you had made a comparison before here and you expect to use the comparison value for a branch or something, don't. Save it, because I will be writing over it. Yeah. Okay. So anyway, how do we implement a lock? This is just our compare and exchange, like the little nice C wrapper for the atomic instruction compare and exchange. So to get a lock, the problem with compare and exchange is it doesn't guarantee that you're going to be able to assign it. Right? It'll just return a 0 if you got it, or a 1 if you didn't, if I remember correctly. So let's see how we implement a lock. Okay, so the lock just looks like this. This is the actual one that contains the value we're interested in. And then there's some debug info that we don't worry too much about. So this was the one that we're going to manipulate with our compare and exchange. And then let's take a look at the code. Oh. Here it is. Okay, we can ignore most of this for now, but this one we cannot. Right. So there is the new value. We're trying to set it to a 1. That's the one that I don't know where that 1 came from in the assembly constraints, but okay. So here we're saying, let's try to swap whatever value is in here for a 1. Right? And if it got swapped, that means it was a 0 before. So it'll return a 0 and then we're good. Then we stop doing this. Otherwise, if it's a 1, well, we try again. So we're trying over and over to set this variable to a 1. If it was already a 1, well, then we have to try again. That's all there is to a lock. All of the rest of this stuff is not important. So it only works because, yeah.
So in Linux, would they have something like that except yield instead of just spin?
So, okay. This is a spin lock. Linux uses spin locks for sure.
Okay.
But spin locks can be expensive. So here's one example. Say you have only one core. And one thread acquires a lock and then gets swapped out because the timer went off. Another thread tries to acquire the same lock. What's going to happen?
It's going to push until the next tab goes on.
It'll just spin here, waiting. How do you pronounce that? Futilely? Anyway, waiting in until a timer goes off again, so that the other thread can finally release a lock. So that's completely pointless. You should never use spin locks unless the thread that's holding the lock at the moment is also running. So you really need to have two running cores for this to make any sense. Otherwise, you really should just go to sleep instead. And we have the implementation of this already. So then we could see if the variable is locked, instead of while like this, we say sleep. And now the program will, the scheduler will wake us up later on. Of course, when you release, you can't just set the lock to 0, which spin lock release would do. Let's see if I find it. Here. Where is it? Wow. Yes, equivalent to locked equals 0. Okay, I don't get that comment.
Maybe it thinks C could possibly load 0 to a register and then move that register. No?
I think this is bullshit. and this is recorded. Hopefully the MIT professor's not listening. I like them. Sorry, Hans. Franz. Franz! Okay. Right. So anyway, we set it to 0. That's all we need to do to release it. So I think we actually have the other one too. We were just looking at it in office hours, and it was called a sleep lock. If you're a sleep lock, well, then you go to sleep, and then when someone releases lock, they better wake you up. Otherwise, you will sleep forever. So let's see. Here's our sleep. While it's locked, sleep. So we're not even trying to set it. Oh boy. Ah! Look at that. Nice. Okay. I thought, what is this? This is not atomic. Right? First we check it up here, and then we set it down here. Take it, that's not atomic code. So we could end up with 2 threads entering a critical section at the same time. Does anyone see why it works?
It's already in its own critical section.
We have another little lock around it, right? So there's a spin lock protecting the wait lock, or the sleep lock. This only works because of this thing. So sleep actually takes a lock and then releases the lock. After it puts the thread to sleep, it releases the lock. And then when you get woken up, you return with the lock held. And next time, I think we'll talk a little bit about condition variables, which are directly related to this wait and sleep, and the importance of checking this. So, but we might as well do a little preview here. So you could say, if it's not locked, sleep, right? Sorry, if it's locked, then sleep. And then once we wake up, we just lock again. So what's the deal? Why do we have a while here? Or how are we gonna, why do we keep checking this thing?
Another thread waiting for the same lock and locking before you.
Exactly. So the wake up could wake up more than one thread. And in general, for these things, there's no guarantees about you only being woken up when the condition is true. You can be spuriously woken up for different reasons. But the most common is you have more than one waiting for the lock. Right? And the wake up doesn't necessarily just wake up one. Maybe it wakes up multiple. Or maybe it wakes you up, but then another thread is coming in just as you're waking up. It just rushes past and grabs the lock, and now you're woken up, right? That sort of thing can happen very easily. This is true anytime you have a condition variable as well. You say condition, wait, blah. You have to do a while loop. So the code should be correct even if you don't have a sleep. This one is correct even if you don't have a sleep, right? Just have a nothing here. You just loop until it's not locked. It'll be very inefficient, but it's fine. Okay, so anyway, there's our wait, and then on the release side, we set it to unlocked, and then we wake up whoever's waiting for it. So this is what you have to do really if you're on a single core and you're working with threads. You have to put them to sleep or you're going to be wasting your cycles. All right, so we're out of time. I think next time we'll look at a few more different kind of lock types, and also in general the problems that we run into with threads. We'll talk about deadlock and live locks and some other race conditions perhaps, and a few other little interesting details. Okay, but please get started with the homework. Let's see, it's due next Thursday. Yeah, that sounds right. There's not a whole lot of code, but there's several changes in different parts of the code that could take a while before you get it right. So, and make use of office hours and such too. I'm not going to be here for the Tuesday office hours, but I'll be here for the Wednesday office hours next week and tomorrow. All right. Yep.
So is it possible for the other thing we saw that was pointless assembly? Is it that arrow notation isn't always going to be a single assembly instruction? Is that it?
But
Or-
yeah, right. So this one here, right?
Well, no, the
It was
one-
essentially this.
Yeah.
Yeah. So sure, this is certainly not atomic.
Right.
But that doesn't matter. What we're saying is we're just assigning this one to 0. The assignment.
No,
Who
it's
cares
not.
if it's atomic? It's eventually going to be 0.
I'm saying for the other function where we had to make that a atomic function and use the inline assembly. It was an arrow notation.
Yeah. So you're talking about the release. Spinlock.c release, right? Where is it? There. This one. Is that the one?
Yeah. Because it says LK arrow notation locked. Is the arrow notation always going to be a single instruction?
No, but we don't care. Because the lock never changes. This is the lock. I mean, that's not going to change. And so the only thing is, could it maybe be unlocked before we unlock it? But how does that work? We're holding the lock. I don't know. I don't think that this is right. Now, there could be some ordering effect here, but we're getting all that here. Like there could be something like, oh, some instructions could be reordered before the release, and that could cause a problem. But with this, this is a mfence instruction, I think, what comes out. I'll send him an email and see if we can see, or check the comments and see who committed this stuff. That's what I'll do. Okay, anyway, I'll see you Thursday.